All right, so welcome and welcome back to this lecture series given by Professor Weinan. He is a professor of mathematics at Peking University and also Princeton University. He has been a pioneer in machine learning and PDEs, and this is the second part of this lecture series, so we'll have a third one tomorrow at 2. And with that, Professor the floor is yours.
Thank you very much. Thanks for the kind introduction. Well, I hope you get something out of the first lecture. Anyway, the second lecture is mainly about machine learning from a PD viewpoint. This is mainly joint work with my former students, Chao Ma, who is at Stanford, and Lei Wu, who is at University of Pennsylvania right now. Okay, so first lecture, we spent a lot of time talking about this particular problem in machine learning, namely supervised learning. And there we are given a data set which represents the function values of a target function that we're interested in at some particular set of data points, xj. And our task was to learn f star, approximate f star. And we do that by trying to minimize what is so-called population risk, which is given by this quantity here, over some function space, which we call hypothesis space. Well, we say it's function space. It doesn't have to be a linear space. It could be just some sort of a set of functions. Okay, this is the one particular example of machine learning one particular kind of machine learning problems that we encounter. There are other machine learning problems. Let me mention dimension reduction. So here we also have we have a set of data points, which are points sampled from an underlying probability distribution mu, and we want to map these set of points to a lower dimensional set. So we want to look for a mapping from R big D to R little d. Hopefully little d is much smaller than big D. And we want the mapping such that it best preserve all the important features of mu. Namely, we should be able to, there should be an sort of an inverse map, a reconstruction map that maps R little d to R big D, such that the reconstruction, namely after mapping, after the first map phi and the reconstruction map psi, the error is the smallest. So this is the dimension reduction problem. Now, you notice that at the end of the day, we're also trying to minimize some expectation. And third example is derives from quantum many-body problem. So we're given a Hamiltonian that represents a quantum system, and we want to look for the ground state. And the ground state is the eigenfunction that corresponds to the first eigenvalue. So by the Rayleigh variational principle, we're interested in minimizing this quantity, and this quantity can also be represented as an expectation. If we define a probability distribution mu, if we define mu this way, then this quantity can be written as this expectation. Now, notice that in this case, the probability distribution mu depends on phi, which is the function eigenfunction we're looking for. And if this is the fermion system, then we also phi needs to satisfy the Pauli exclusion principle. Well, if it's bosons, it also needs to satisfy exclusion principle. Namely, for fermions, phi needs to be anti-symmetric. For bosons, phi needs to be a symmetric function. So in this case, we can also write the objective function as an expectation. My third example is a stochastic control problem. So this is the dynamical system that defines some state we are interested in to control. Here, psi is the random noise, say IID noise. A is the control, S denotes the state. And we want to select the optimal control such that some objective function is minimized. Again, this is an objective function is an expectation over all possible noises. And then we have some running cost plus some terminal cost. Okay, so in all these examples, the objective function we're interested in can be expressed as an expectation. And these are kinds of examples that we have in mind. Now, our objective is to formulate a nice continuous problem. I put nice in quotation mark because we don't really have a specific definition of what is supposed to be nice. So, but we want to formulate some nice continuous problem and then discretize that continuous problem to get concrete models or concrete algorithms. So this is the kind of path we follow when we solve physical problems. We first find some sort of mathematical formulation of the physical problem, either in terms of PDEs or in terms of some variational problems, and then we discretize and get the algorithms. So we want to do the same thing. In the case of PDEs, nice means that the PDE needs to be well posed. In the case of calculus or variation problems, nice means that it needs to be in some way convex and needs to be lower semi-continuous. In this case, one can show, under suitable definitions of convexity, one can show that there exists a unique minimizer. Now, for machine learning, when we say nice problem, we have in mind that the variational problem that we get in the end, I give you 4 examples in the last 2 slides. These kinds of variational problems has a simple landscape. We don't want the variational problem to have lots of bad local minima. That would be bad. So we want to have a simple landscape. But what does simple mean is subject to further investigation. But this is sort of the vague idea we have in mind. Now I'll discuss how we're supposed to do that. Now let's take a look at traditional numerical analysis. So what was the standard practice there? So let's take this example of a simple variational problem we want to solve. Now, there are 2 ways to do it. One is to discretize this variational problem, say using some finite element, piecewise linear approximation. And then after discretize this problem, we get a discrete optimization problem. In this case, it's actually a quadratic problem. And then we solve that quadratic problem, variational problem, by some optimization algorithm, say gradient descent. So that's one way to do it. The second way to do it is to write down some sort of gradient flow for this variational problem. For example, this little gradient flow, in which case, in this simple case, it's just a heat equation. And then we discretize this gradient flow, okay, by finite difference or finite element. And we recover some kind of a variation, some kind of a gradient descent algorithm. It doesn't have to be gradient descent algorithm, but we recover some algorithm for the original problem. So there are 2 different ways, depending on the order in which we formulate our gradient flow or discretize. For machine learning, we can take both approaches. Now, a key notion here is how do we represent functions? I made a point at the end of last lecture that in machine learning, we typically try to represent functions by some kind of expectation. Here again is that same point. Now, suppose we represent functions by Fourier transforms. This is a very popular way to do it. And then we discretize this continuous Fourier transform by some discrete Fourier transform. Now, this works perfectly in low dimension, but in higher dimension, this kind of approach suffers from curse of dimensionality, as I illustrated in the first lecture. But suppose instead our function is represented in this form. Here we replace d omega by pi of d omega, where pi is the probability distribution, and that's the only difference. Then this function can then be represented as an expectation. Associated with expectations, a very natural way to discretize expectation is the Monte Carlo sampling. So we would take an IID sample of omega and then discretize this expectation by an empirical sum like this. And we know this simple calculation gives us that the convergence rate is independent of dimension. And this is very important. And we also mentioned this point in the last lecture. But what's important here is that this guy, this discretized form, discretized approximation, is nothing but a two-layer neural network. I can write this in this form, where sigma is this activation function. This is particular exponential activation function. Then I can write this guy in this form. And this form is nothing but a two-layer neural network, as we saw in the last lecture. So the point being made here is that if a function has a representation like this, then it can be approximated by a two-layer neural network with a convergence rate that's independent of the dimensionality. And that's a very important point. So that's why we're interested in representing functions like this. Okay, a slightly more general way of writing this kind of representation would be this. So here we're writing, there is a coefficient A, and there's some activation function sigma, and then there's some probability distribution pi. So we're interested in representing representations in this form. Now, in the context of machine learning, we need to decide which set of parameters are going to be regarded as being parameters. So I have a theta here. That's a generic notation for the parameter that we're going to be looking for in the particular machine learning model or machine learning algorithms. Now, in this representation, or more generally, I can write this representing in this way. If I define rho to be sort of the probability distribution over the extended parameter space. So here, sort of pi is just the projection of rho onto the W space. So this can be written this way. Now, in this setting here, I can regard A as being the parameter. I can regard pi as being the parameter. I can also regard rho as being the parameter. In a different choice of theta would correspond to a different model, as we're going to see later. So once we've decided what representation we're going to take, then the objective function is just this kind of objective function. So this would be the objective function for the supervised learning, and this is the objective function for the dimension reduction problem. May correspond to different thetas for phi and psi, and this is the objective function for the quantum many-body problem. Okay, then we can discretize. So, for example, the Fourier method would correspond to discretize this probability distribution pi. Let's take pi to be the parameter. They're going to be optimized over. So we can discretize pi by this kind of empirical distribution where omega j lives on a uniform grid. This will be a Fourier method. And then the function that we get will be this. And that will be a traditional Fourier method. Now, in the particle method, which will be the dynamic analog of Monte Carlo, and we know Monte Carlo is a good thing. Particle method is nothing but a dynamic analog of Monte Carlo. We discretize rho by this empirical distribution, and these guys are called particles. Aj and omega j, these guys are called particles. And then the function we're interested in, the function represented by this particular discretization is this. And we are interested in optimizing, find the optimal set of, particle distribution. And this will be the two-layer neural network model. Okay, now, and we can apply the same strategy for different variational problems. Okay, now, and then once we've got the variational problem, discretize the variational problem, we can either use gradient descent or stochastic gradient descent to discretize. we can readily use a stochastic gradient descent because our objective function is an expectation. So very naturally, we can use stochastic gradient descent. That's why I made the point of that the objective functions we're interested in optimizing is our expectations. So that's one way to do it. So that's sort of discretizing the variational problem and then apply gradient, some sort of optimization algorithm. Another way to solve these kind of problems is to define some continuous gradient flow. For example, imagine we represent f in this way, and here we have two sets of parameters. One is a, one is pi. In order to write down the gradient flow, we need to treat a and pi differently. For example, for a is the so-called non-conserved order parameter. A is some arbitrary function. In the context, if we make an analogy with non-equilibrium statistical physics, A would be called non-conserved order parameter, and pi would be called conserved order parameter, because pi is a probability distribution, so the total integral of pi needs to be 1. So for A and pi, when we write down the gradient flows, we need to do it differently. For A, since it's non-conserved, we can just do the simple L2 gradient flow, and this is also called model A dynamics. And that's how Allen-Kahn equation was derived. So for those of you who are in PDEs, you're familiar with Allen-Kahn and Kahn-Hilliard. So this will be Allen-Kahn. But for pi, which is conserved, we need to define the gradient flow differently. And this is called the model B dynamics. And here the recipe is as follows. We first define the variational derivative in the usual way. And this is actually called chemical potential in physics. And then we define the velocity by the negative gradient of the chemical potential. And this is called Fick's law in physics. And then we define gradient by density times the velocity. And then we have the continuity equation. And this is called the model B gradient flow. And this is how Kahn-Hilliard equation was derived. Now for this model B gradient flow, okay, before I talk about the specific examples of the model B gradient flow, let me first make a remark about model A gradient flow. So in this case, we fix pi. We only make A to be the parameter we're minimizing over, we're optimizing over. And this is if you remember the first lecture, this is a little bit like the random feature model, and it's a linear model. So for this linear, and the gradient flow becomes a linear integral equation like this. It's just a linear integral equation where the kernel is defined as the expectation of the product of the activation function over the sample. So this is the linear integral equation, and the kernel is symmetrical positive definite. In this case, one can show that there exists a Lyapunov function, and this is the Lyapunov function for the coefficient. And for this Lyapunov function, you can, well, to define this Lyapunov function, let's assume that our target function has this representation, and the coefficient is A star. Any A star would do. So, and then we can define the Lyapunov function this way, where R is just the population risk. And then one can show that this is indeed a Lyapunov function from which we conclude that the population risk decays in time, like 1 over T. So this is due to the convexity, actually, of the problem. Now, let's now look at this case, the second case, the model B gradient flow dynamics. In order to look to examine that situation, let's look at a slightly more general representation. So we're writing this the function f is represented as an expectation of some more general feature function. So phi is a more general feature function. So before we were looking at this particular feature function, A sigma omega transpose T. So for two-layer neural networks, phi takes this form, and U would be like the A and W, use the parameter. But it doesn't have to be like this. We can look at more general feature functions, okay? And then take rho to be our parameter, the parameter we're interested in to optimize with. And obviously rho is conserved, so we should write down the model B dynamics. And the model B dynamics, it takes this form. It seems to be a nice looking PDE, but it's not really a PDE because V is given by this, the variational gradient, and it's got an integral. It's got two terms. One is related to the target function. The other is given by the kernel. It has an integral form given by the kernel. So this is sort of an integral differential equation. Now, several remarks are in order. The first is that this is nothing but the gradient flow of the population risk under the Wasserstein metric, and this is very well known. So this is the gradient flow under the Wasserstein metric. And second is that this equation is the same as the mean field equation derived by several groups of people by studying the continuum limit of two-layer neural networks. So this is a very nice set of works that look at two-layer neural networks and derive the continuum limit, and they recover this equation, these equations. And here we are looking at differently. We started from continuous viewpoint, and then we get this equation just by following the standard recipe of writing down gradient flows. Now, because this is a nice looking gradient flow under Wasserstein metric, we were hoping that all the machinery coming from optimal transport theory would be useful here. So far, this has not been the case. So far, there has not been a lot of application of powerful, the powerful machinery from optimal transport. And the main reason is that these problems do not satisfy the so-called displacement convexity. And that's bad. So without displacement convexity, all these machineries seem to be out of the window. And that's a pity. And that's something which, the community is still working on, trying to find ways to make use of the mathematical machinery and to analyze this set of equations. I personally feel that this is a very important, interesting set of equations. The one result that I want to mention is this result by Shazan-Bach and further improvements by Stefan Wojtowski, my former postdoc. So this is sort of a complicated looking theorem, and it actually has more conditions that I didn't even write down, some more technical conditions. But the gist of the theorem is the following. Under the following condition, under this condition, namely that the initial density, initial distribution, sort of the support of the initial distribution covers the whole space. So here is a special form. So we're assuming that it's got a, we're assuming that every open cone in this set has positive measure with respect to rho 0, and that's the support. That's one way to formulate the support condition I just mentioned. Anyway, on that under that condition, so this one bad situation would be that rho 0 has finite mass. That would be bad. So if the support of rho 0 is the whole space, then if rho t converges, if there's convergence, then it has to converge to a global minimizer. So this is the gist of the theorem. So assume convergence, then it has to converge to a global minimizer. So a natural question is, can we prove convergence? So we have not been able to do this. Of course, there is another question, which is, if it indeed converges, what about the convergence rate? Does the convergence rate suffer from a curse of dimensionality? That's also another important question. So anyway, this is it seems to be one non-trivial result that has been obtained from this kind of a PDE continuous mean field approach. Okay, now having got these PDEs, we need to discretize these nice PDEs. Well, first we need to discretize the population risk. That's because that's a continuous form. Well, that's easy to do. If we use training data, we discretize population risk into empirical risk. That's trivial. And then we need to discretize the flow, the gradient flow. Well, there are several ways. There's particle method. I already give some introduction about the particle method. There is also smooth particle method. This is like the vortex blob method in computational fluid dynamics. Or sometimes we're also interested in solving these problems in low dimension. In that case, spectral method is not a bad idea. Okay, so let's look at what happens if we discretize using the particle method. So, well, first, let's look at this, the linear problem, the random feature model. So that was the integral equation, linear integral equation. And this will be discretization by particle method, replace pi by this sum. And then the Wj will be called the particles. The value of A at Wj, let's call that Aj. Then this PDE after discretization, this is the integral equation after discretization becomes this dynamical system. And this dynamical system is nothing but the gradient descent dynamics for the random feature model. So going through this particle method, we recover nothing but the gradient descent dynamics for the random feature model. Now let's look at the conservative flow. This is the conservative flow. If we discretize by the particle method, namely replace the probability distribution rho by this empirical sum, over the particles, Uj will be called the particles. Then we have the following little lemma. So in order to state the lemma, let's note that for if rho is replaced by this, then the function that represented by the continuous representation is replaced by this. And then this function depends on the position of the particles. And the population risk in this case is the function of the particles. And let's call that function I. So this little lemma says that, as a matter of fact, if we take the initial condition to be a sum of delta functions, then the solution to this little PDE, actually integral differential equation, is also given by a sum of particles, empirical distribution over some particles. And these particles follow, the dynamics of these particles follows the gradient descent for the objective function I. So what I'm saying is that this flow, this continuous flow, in this situation when the initial condition is a bunch of delta functions, is a sum of delta functions, this continuous flow actually reduces to nothing but the gradient flow for the finite particle system, namely finite neuron system for the two-layer neural network. And this reduction is exact. You don't need to take any limit on, there's no discretization error involved. This is the reduction is exact. And the implication for this is that if we go back to these papers that I mentioned, that these papers where they studied the continuum limit of two-layer neural networks, actually you don't have to take the continuum limit. Even for a finite neuron system, if you define the rows and the V's in the natural way, then you'll find that the gradient descent dynamics can be written as this continuous looking PDE. So this continuous limit is actually exact. You don't have to take the limit. Okay, that's what I'm saying here, that the continuum PDE reduced to the gradient descent dynamics for finite neurons. Now, if we, and then let's take a look And what happens if we run this numerically? So what's shown here in the left is the heat map for the testing error in terms of log M and log N. Remember M from last lecture, M is the number of neurons, number of free parameters. N is the signing of the training sample. And you can see that we have some sort of a nice smooth distribution. And it's not so surprising because everything here is nice and smooth. Now, if you compare this with the conventional setting, the only difference is that instead of writing F like this, we write F like this. This is what people do in practice. Very few people do this. Although this is very naturally suggested by either the continuous viewpoint or the mean field viewpoint. Okay, so this is what people usually do. If you look at, for this conventional neural network, the two-layer neural network model, if you look at the heat map for the testing error, and then you see a phase transition. You see, so there's a nice phase where the test error is small, and there's a phase, bad phase, for which the test error is big. And if you are not so lucky, if you pick your M and N that falls into this part of the the phase space, then the performance wouldn't be good. So this is only for two-layer neural network. One can imagine that if we have many layers, then this diagram would be much more complicated, and then it's a much harder task to select your hyperparameters to fall in the nice region. Okay, this is a sort of a conjecture that why it's so hard. The performance depends sensitively on the choice of the hyperparameters. Okay, so now moving on to flow-based representation. So back several years ago, for a little bit more than 4 years ago, I proposed that we can look at machine learning from a continuous dynamic system viewpoint. Namely, we can construct functions, nonlinear functions in a hypothesis space using a flow. If we consider nonlinear ODEs, and the flow map is a nonlinear map. And if we just contract that nonlinear map by some vector, we will get scalar functions. And then if we put enough G's right-hand side, we will be able to generate enough nonlinear functions this way. So this is another way to come up with the hypothesis space in machine learning. And this is also discussed, this sort of idea is also discussed by Haben and Rosotto, and it's now popularized by the so-called neural ODEs. This, essentially the same ideas was rediscovered in later in in the machine learning community, and it's called neural ODEs, and this is actually much more popular than the original paper that we wrote. Anyway, so let's look at, this is another way to represent represent functions through this kind of a flow. But the natural question is, how should we choose the right-hand side G? What would be a natural representation of G? Well, we claim that the natural representation of G is this. Well, if you look at it, it's nothing but the kind of representation we're looking at before, except now these guys, A's and Pi's, all depend on this additional parameter tau, which is like Soto time in this flow. It's a bit like a time, we call it Soto time in this flow. So I claim that this is the natural representation. So why is this the case? Why is this the case? So why do we make such a claim? Well, before I go on, let me just mention that this representation can also be, we can also replace pi by rho, just like before. Whereas where rho is the probability distribution in the bigger probability space that includes A. So coming back to the question, why do we claim that this is a natural choice? Well, let's discretize. Let's think about discretization of this. Well, if we discretize, we would essentially have some sort of residual neural network. So this would be some sort of a residual network. It's just discretization of that ODE. And let's look at this residual neural network. Let's assume that, here I just rewrote this residual neural network. Let's assume that these parameters A's and omegas are IID random variables sampled from a particular probability distribution rho. So let's assume this is the case. Then one can show, simple theorem, that as the discretization, as L goes to infinity, or M goes to infinity, or L and M goes to infinity simultaneously, then this flow, these Z's converges to a continuous flow, and for which the right-hand side is not replaced by this expectation. And this is some form of law of large numbers. The law of large numbers happen here. So this gets replaced by an expectation. So this is why I claim that G, the natural choice of G, is this form. Of course, here we made the assumption that these guys are sampled from a fixed probability distribution, rho. And if we allow rho to change nicely in tau as a function of tau, then we would get this more general form where rho depends on tau. And this is a similar kind of thing. So anyway, this is why I claim this is the right form. Now let's look at this form. Again, let's look at a more general, slightly more generalized form where we put in a more general feature function, phi. This is the same story as before. Let's consider this dynamical system, and then we get the functions in hypothesis space by summing over all the components. And we're going to view this as a control problem where the controls are these probability distributions rho. So there's a one parameter family of probability distribution rho, and these are the controls, and Z would be the state. And we want to choose these controls to minimize this objective function, namely the population risk. So this is the control problem. In control problem, we have two set of tools. One is the Hamilton-Jacobi-Bellman equation. Now that would be terrible to write down because of the fact that the controls is a set of probability distributions. So the Hamilton-Jacobi-Bellman equation is a huge equation. It's not very useful to write it down. Another important tool is the maximum principle, the Pontryagin maximum principle. And let's look at the implication for the Pontryagin maximum principle. In order to define the Pontryagin maximum principle, we need to look at this state, co-state, and controls, the product space of states, co-states, and controls. And then we define a Hamiltonian over that state. And here, remember the control is a probability distribution. So P2 stands for probability distributions with finite second moment. The Hamiltonian then is a function defined over the state, co-state, and the control, and is defined this way. Just the standard recipe, follow standard recipe in control theory. Then Pontryagin maximum principle says that the optimal control, rho, maybe I should put rho star here. The optimal control is an argmax for each, sorry, let me go back. The Pontryagin maximum principle claims that for each subtle time tau, the optimal control is an argmax of this expected Hamiltonian in which the state and co-state satisfies this forward and backward equation with this boundary condition. So this is nothing but the Pontryagin maximum principle, Pontryagin is the maximum principle stated in our particular setting. Okay, we can also try to write down gradient flow. In order to do that, all we have to do is to replace this guy by the gradient flow, By the way, maybe I should add one more remark, that this quadratic maximum principle is very much like the KKT condition, because of the fact that remember, the KKT condition is, it's like a stationary point kind of condition, gradients being 0. Here we have a slightly stronger conclusion than KKT condition, and that follows from the fact that we have a continuous. Our problem is sort of a continuous setting, and therefore we can claim that actually there's argmax here for each tau. So this is slightly stronger than sort of this standard KKT condition. But anyway, quadratic maximum principle has the flavor of a KKT condition. Now, in order to define the gradient flow, we just have to replace this by the gradient flow. Okay, so for example, KKT condition might conclude that this thing is equal to 0. And whereas quadratic maximum principle says that this is actually argmax. Anyway, now this would be the gradient flow. It's a one parameter families of gradient flow coupled by this, backward and forward equations. So this is another model. So either we have this model, the gradient flow, or we have this model, the quadratic maximum principle. And our next task is to discretize these guys. First, let's look at how to discretize the gradient flow. Now, in order to discretize gradient flow, we need to discretize these guys. We just discretize these ODEs by forward Euler and backward Euler. Then we discretize this guy by the particle method. This will be the natural thing to do, and that's described here. And then the same story happens here as what we saw for two-layer neural networks. Namely, we recover the gradient descent algorithm together with the back propagation for resonance, for scaled resonance. So the continuous description gives us naturally the gradient descent algorithms together with the back propagation for the resonance. Now, for the maximum principle-based training method, we can go back. It's also straightforward to discretize these guys. We just discretize this by forward Euler, backward Euler, and then we do argmax of this. And turn out, if we do that, it doesn't work out so well. And we found, we meaning Chen Xiao, Li, Long Chen, and Chen Tai, and myself. Actually, Chen Xiao is pretty much behind this. Pretty much the person who was behind this. We found that if we do an if we define the whole thing in an extended state and co-state space by introducing some auxiliary variables V and Q, that sort of represents these right-hand side PDEs, the ODEs, these equations, how much these equations are satisfied. We would write it out. Okay, so we sort of penalize how much the equations are satisfied. Then we do the standard forward and backward equations, and then the argmax. And then the performance is quite remarkable. And here are two sets of examples. On the top, we have sort of a nice initialization. We're comparing the maximum principle-based algorithm, the performance of the maximum principle-based algorithm, together with the stochastic gradient descent. So SGD, eta grad, ADAM, these are the most popular versions of the stochastic gradient descent. This is training error, this is testing error. The top, we have a nice initialization, namely we initialize by some Gaussian with a small variance. And the bottom, we have sort of a bad initialization in the sense that it's initialized with a large variance. And in both cases, you'll see that the convergence rate, either the training loss or the testing loss, for the maximum principle-based algorithm, it converges much faster than the stochastic gradient descent. Now, at the moment, these algorithms are not optimized. So therefore, the wall clock is actually comparable. The cost of performing the minimization at each step is still too heavy. But we believe that there is room for improvement. In any case, these two most important ideas, namely maximum principle based formulation or stochastic or gradient descent based population, that's the main difference between the two. And what we described, the maximum principle method and the usual gradient descent or stochastic gradient descent are sort of two extremes of discretizations of these algorithms. You can think about, the two extremes. One being that you perform backward and forward propagation for each step of gradient descent, and the other extreme being that for each step of a backward and forward propagation, you perform the optimization to convergence. Okay, so these are the two extremes. If we assume that each forward and backward propagation, okay, for every k steps of optimization, there's one step of forward and backward propagation. Then GD and SG corresponds to the case of k equal to 1, and maximum principle corresponds to the case of k equal to infinity. So namely, you have many steps of optimization. So these are two extremes. Okay, now you can do other things. For example, you can, as before, you can sort of fix pi and only let A to be the variables, to be the parameters you're optimizing over. And this will be some sort of a flow-based random feature model. And this performance is not so bad. We tried, but we didn't try very hard, but the performance doesn't seem to be very bad. And this is could be a potentially interesting model. So let me summarize. Continuous formulation tries to formulate the first principles of machine learning. So we're trying to sort of, whatever that means actually, give rise to new variational and PDE-like problems. The performance of these algorithms are more stable to the choice of the hyperparameters. There's no phase transition in the performance of in the testing error over the state space. It gives rise to new models and new algorithms, maybe more suited to specific applications. But maybe more importantly, it allows us to think about machine learning outside the box. So when we think about machine learning, we kind of got stuck with neural networks. And this continuous formulation allows us to sort of think about machine learning outside the box. And the crucial point here, the most crucial point, is the representation of the functions as some forms of expectation. So we had we discussed two kinds of representations. One is the integral transform based, and this is very much related to two-layer neural networks. And then the other is the flow based, which is very much related to residual neural networks. And however, we can come up with other natural training algorithms, such as maximum principle based training algorithms. And there's one question we don't know how to address. So what about multi-layer neural networks? So 3, 5-layer neural networks. How do we make a similar story in that situation? Are there other representations? Are there other ways of representing functions as expectations? And then if you think back, you find that in a way, neural networks are very natural. If you think about this continuous viewpoint, you find that the simplest continuous viewpoint, after the simplest discretization, what do we get is nothing but the neural networks. So neural networks, in a way, are actually very natural. And that's an interesting point. This is all I want to say. Thank you very much for your attention.
Thank you very much, Professor, for a very interesting talk. I think what we do is that we ask the audience here first, and then I can see that there's already questions in the chat. So any questions? Any questions here? No? Okay, so I'm going to moderate the chat so I can see that there's at least two here. So Yuri Korolev, you have two questions, right?
Yes, well, I discussed one of them with Bangti in the private chat, but still maybe we could discuss it further. But the first question, well, thank you for the very interesting talk, first of all. I really like especially the flow connections with the flow. My first question is about the Pendragon maximum principle and the algorithms you derived using that. I suppose this is related to the Bellman equation. Is it exactly the same thing, or is it something slightly different?
This is not. This is different from the Bellman equation. The Bellman equation would be terrible here because, the Bellman equation would be terrible here because this Bellman equation would be too big. It's over huge space.
Okay.
So actually, we have a paper that discusses mean field control viewpoint of this of deep learning, in which we wrote down a Bellman equation, and then you see that it's a terrible looking equation over the huge space. And then the maximum principle is much more productive.
Okay, thank you. And the second question was about the slide 28, I believe, 27, 28. Yes, exactly, 27. So you have this penalized objective in a way, and my question was whether this is somehow related to augmented Lagrangian methods. Although Bangti Jean wrote me in the private chat that probably not, because you don't have any multipliers here, but still.
You could say that. You could sort of view these as constraints, and this is a little bit related to that. So Q, so this it corresponds to this term, and this corresponds to this term. So you could say that. I mean, I think it's motivated by that, but I don't know whether it's so why this performs much better than that by the standard than this. It's not 100% clear to me.
Okay, thank you so much.
I think that's a mystery.
Right, so please write in the chat if you have a couple of questions. In the meantime, I have a couple of questions.
Please.
So you started with these very nice examples where you sort of show classical numerical schemes and what we can do with this machine learning approach. So a lot of the classical numerical methods would come with some kind of guarantee that here is the error, I have a step size, I have a certain function class, and so on and so forth. How does this relate in that case? Can one also come up with guarantees that says that, okay, if I run my algorithm in this way here, I will get an error of this form? Or is that sort of the big missing piece? Or what's your perspective on those kinds of things?
Okay, that's a very good question. In classical numerical analysis, right, take a finite element. So we get these convergence rates, and then we say, well, conjugate gradient would do when we try to solve the optimization problem. And if we linearify elements, for linear PDEs, yes, because the quadratic, that's it. For nonlinear PDEs, we didn't come up with any sort of a non-trivial theory. We kind of say, okay, as long as the solutions are for nonlinear PDEs, the solutions may not be unique, as long as each solution is kind of isolated, and the non-degenerate pretty much is very much like a linear story. We didn't sort of come up with any theory about the global convergence or anything like that, because it wasn't so important. We can always sort of put our initial conditions sufficiently close so that nothing bad happens. That's not the case here. Here, the minima, global minima is almost always degenerate, and the landscape is very much non-trivial, and we don't have a good understanding of that. So That's the essential bottleneck. Other than that, I think as far as the approximation theory is concerned, probably it's not that different from what I discussed in the morning.
I see. So one more question I have. So you showed the Hamiltonian in the beginning. So you want to get the ground state of the Schrodinger operator, which is a highly non-trivial thing. And this is really where you see this kind of dimension reduction idea really being fruitful, because, you know, you do standard methods on this end and you're toast, you know, in even, you know, very, very simple molecules. So the issue is this. In that case, you can sort of always measure the error. So if you have a candidate, you can also plug that into the equation and it will always become an upper bound. So you don't make a mistake, if you will. So the computations that you'll do, regardless if you have error bounds or not, the value that you're going to get will always give you an upper bound. And that gives you some kind of error control. So my question is, that is a typical case for which, regardless of the optimization methods of what you're doing, you will never make a mistake. You'll always get an upper bound for the ground state energy. Are there other cases in either PDE theory and other areas for which you can see that there is a way of checking what you have? So you may not have a perfect convergence theory, but there's some kind of residual, there's something that you can do to test it. So we'll give the physicist or the numerical analyst a way of assessing the output in some way.
Well, I guess any variational problem has that property, right?
Yeah, so checking the residual will give you a, yeah.
Mm-hmm. But you know, the problem, okay, actually, the quantum many-body problem is a very exciting active area of research right now. The problem there is that, okay, it does give you upper bound, but the upper bound might be pretty bad. So,
you know, I completely understand that, but if a classical method gives you a number and you know, you can't squeeze more out of the computer, and you run this method and you can see that that number is lower than the other one, you've still achieved something, although you cannot say, oh, you know, I know that I'm epsilon away from the true thing, because nobody will be able to do that.
Yes, I agree. Yes.
So, but I have one more, let me see if there's other questions in the chat. I don't want to take over completely.
Mm-hmm.
So there's one other question regarding the issue of the lowest eigenvalue. Could one use a simple matrix problem as a toy model to understand this better? It's actually not a complete toy model. If you want to understand the lowest eigenvalue of a large matrix, that's still non-trivial. Is it possible to do this in that setting? Because, you know, the Hamiltonian in infinite dimensions is much more complicated beast. Is it possible to do this as a toy model to get an understanding of this with simply a finite dimensional matrix instead?
Okay, that's a good question. I haven't thought about it. I was going to
assume that's easier to understand. I can even start with a 2x2 just to get a feeling, and then I can blow up the dimension. But as long as it's finite dimensional, I have much more control compared to the pretty wild beast the Schrodinger operator can be.
How does neural network come into play if you have a 2x2 problem?
Well, I mean, I can still try to minimize over some functions, right?
Oh, okay, sure. So like type binding model. Sure. Yes. Type binding model is like that. Quantum mechanics. Mm-hmm.
So I was just thinking, is there a way that one can start with simpler problems to understand? Because right now, my understanding is that it's really, really hard to get a feeling of what we're actually doing. We can minimize, and then in certain cases you can test. But the problem is, can we actually get some more understanding to play with this in a more control environment? That would be my overall question, if you see what I'm.
Okay. There are some progress. I mean, it's not like, okay, this is what I want to talk about in the next lecture. So if we think about solving PDEs problems, you know, solving PDEs using machine learning based algorithms, and there are some progress towards understanding the error. So I'll mention that tomorrow. although, still very preliminary. The difficulty is always associated with the training. For the training part is the difficult part. For the training part, even simple supervised learning is a problem. It's hard to be much more simpler than that.
Indeed. Okay, if there are, I'm just going to check if there is any more questions. And I don't think there are, so I think we should thank Professor again for a really, really interesting talk. Thanks so much.
Thank you.
And then we'll reconvene tomorrow at 2 p.m. local time. And then we have the last and final lecture in this series. Thanks a lot.
Thank you. Thank you very much.